so so the idea then is that we want to find what this would be called. This would be called volume of solids of revolution. So if you think about, you ever, at Hobby Lobby, at the party, you get those party decorations that are folded flat, and clip it, and they fold out and make a bell or a, whatever, some kind of party decoration, a cylinder, a ball, whatever. That's kind of what we're talking about, right? We're taking a two-dimensional flat area and revolving it into a three-dimensional shape. So by laying the lemon flat on the surface this way, we can think of taking this region right here and revolving it. That's this arrow. So that's what you'll hear in the problem. It'll give you a region like we've been talking about. Like here's this region. We've been finding the area of that region. Now they're saying take that region, revolve it around an axis, create a solid, now find the volume of that solid. So if we think of this, it looks like this then. We take the top half here, we revolve that around, we can envision this three-dimensional thing being created, and then here is one slice of that. So what we basically did here, and you get to the end here, we get into this infinite summing process. We've talked about the integral as an adder. And so what we're doing is we're saying, okay, you guys created 6 slices, and you added up their volumes, and then you compared that to your displacement. But what if we did 10 slices? And we talked about how the slices aren't really cylinders. They're more like this, right? Because this thing changes, right? So if you have a significant width, the radius on this side of the slice is going to be different than the radius on this side of the slice. But what happens when you do 10 slices? What happens when you do 100 slices? What happens when you do 1,000,000 slices? Pretty soon they're paper thin, right? They're paper thin. Now, aren't they pretty much cylinders, right? The thinner they get, they would more and more resemble cylinder slices, right? And then, of course, if you have an infinite number of slices, then all of a sudden that thickness goes away. That's that part that becomes the dx. And now we would just call them circle slices. It's almost like they're so thin, there's no width, they're almost just two-dimensional. Now we can just call them circles. Okay? And of course, the area of a circle, well, the volume of a cylinder, of course, we said, well, I should write it up here. The volume of a cylinder, as you guys wrote in your worksheet, is pi r squared h. But this is what becomes the dx, right? And of course, that's just a geometric fact that when you have a three-dimensional prism that maintains its shape throughout, in other words, we have circles. As we slice this, we have circles all the way through, that you just take, the formula actually in geometry is this. Big B stands for the base area times your height, and then that gives you the volume of the prism. And so this is our area, and then this becomes our width and thickness, and that gives us our volume. So it's kind of like, centimeters squared times centimeters, and that gives us our centimeters cubed, okay? But what we're doing here is we're saying, so a way to find volume is to add up the volume of all the slices, right? Well, if you have an infinite number of slices, it's really like adding up the area of all of them with a teeny tiny bit of thickness, right? This thing that goes away, the dx. Okay? All right, and so that's what you came up with here. And so your integral for some of you ended up being 0 to, 7.2. And then the area is this, pi, and then this is the thing I talked with all of your groups about, the strip. The strip, right? We've been talking about drawing these regions and then putting in a strip. This strip, if you look right here, this strip is what? It's the radius of the slice, right? This strip is the radius of that slice. And so this y, and of course, how do we get the length of the strip? We do top minus bottom. Now, we didn't talk about top minus bottom here, but we really could have said, well, that's f of x minus 0. Because what we're going to do is we're going to have regions that are not setting right on the x-axis. We're going to have strips that are between two curves, okay? And so we'll do top minus bottom, right minus left, because we're going to have some horizontal things too. We're going to talk about regions that revolve this way, okay, and revolve around a vertical axis, and so all of a sudden we're going to have horizontal strips, okay? So we'll get into that more on Friday, okay? So we'll keep it pretty simple right now, but this function value, this strip, y value minus 0 is our radius. So our integral is going to be pi, and then our f of x, which on our calculator we call that r of x, and then our dx right here. But you can see how that's going to give you volume, because right here, this is going to give you centimeters squared. The dx is like centimeters, and so that's your width, and that gives you centimeters cubic, and that gives you the volume of that thing right there. So now, a lot of you were not very close, right? When you type this into your integral, now you'd probably use r of x, because we had back here, we called that r of x. So on your calculator, you type in this integral. So on your calculator, you type in that integral from 0 to 7.2 or 8.7 or whatever you had, times pi times r of x squared dx. Okay? And did anybody get very close? A lot of you were 200 and something on your lemons, right? 200 cubic centimeters. The displacement's probably the best. The slices, depends on how good your slices were. What was the closest anybody was? I saw somebody was like about 20. On your I'm talking your slices and your displacement, not your integral. What were you guys, 40? 20? 90? Okay. What were you guys? 50. Okay, and that's pretty typical. And there's a lot of room for error. The slices weren't all really great looking, right? So that was interesting. Displacement probably the most accurate. This one has a lot of room for error because we were tracing the lemon. So how accurately we trace? You got the width of the pencil. So maybe your thing was really taller than the actual lemon was. Did you get it right in half? Is the lemon really symmetrical? Really, what you're assuming there is you take the top half and revolve it, and the bottom half's exactly like the top half. And that isn't necessarily true on these lemons either, right? So there's a lot of room for error on this process here. Okay, and you say, well, geez, you think this is the calculus stuff, this should be best. Well, you would have to get, an engineer who would want to do this. I mean, let's say you're going to make a part. Let's say you're going to make something. I've got some examples I'll show you on Friday. But let's say you're going to make something, and it's a big part. You want to do a cost analysis. How much material are we going to need? You need to know the volume of the piece, the volume of the solid. Okay, now when we talk about these, we talk about volume of the solid. It's not like volume of this beaker, like empty space. The volume of this beaker is how much empty space is there, how much can we fill up. We're talking about the volume of the solid material, right? The lemon is solid all the way through. So what's the volume? So you'd be wanting to know what's the volume of how much plastic do I need to make this part? And so before you even make it, you're gonna have a computer generated. You're gonna use mathematical modeling to create the shape of it, and so you'll have a much more accurate depiction because that's what it's based on. And then you can run this process and you can see the volume. Okay, displacement doesn't do you a lot of good when you got a great big thing, and it's not even a physical thing. It's just made up on the computer as of right now. So how are you going to do displacement on that? The great big tub of water, you make one, and then So this has a lot of good uses. To be able to do it this way. So let's look at what the problems will look like for you. So here's an example. So let's say we had y equals x squared plus 1. So I don't know if you want to jot this down in your notes here, maybe just a little bit, because this will lead into the homework. There's about 5 problems to do. They're pretty easy if you have the hang of it. It's one of those things, to be honest with you, that you think should be hard. And at the end of the day, your greatest fear probably is making it too hard, right? You'll do it and you'll think, well, geez, this seems too easy. And it really is pretty easy. Okay, so let's say you had this region right here. Let's say you had y equals x squared plus 1. We had this blue region, which I'll write out for you here in a minute. I'll write it out for you in a minute. And we were going to revolve this around the x-axis. So it would create some sort of shape kind of like this, kind of a bugle, I don't know, kind of a trumpet, I don't know, shape, whatever, I don't know. But it would create that. Well, you can see this slice. We got one slice here in the middle of it. Right? And so the idea would be to add up the volume of all those slices, right? Add up the volume of all these slices here, okay? So, kind of like going through here, right? Add up the volume of all those slices. So that's what we'd be looking at, okay? Well, you're not going to have the advantage of having these 3-dimensional shapes here. So when you work a problem like this, so this would be, this would be an example of this problem. So it'd be, okay, so if you want to write down kind of a formula, this is kind of our formula right now. Now the only slice we're talking about at this particular time is a circle slice. So for us, the area of a circle is pi r squared. So that's the only thing we need to worry about right now. Now on Friday, we'll talk about other types of slices. Okay, what types of cross sections, could you have? You have a lot of different types of cross sections. We're going to deal with about 5 of them or so. Okay, but right now we're talking about circular slices. So your problem would look something like this. So they'd say, okay, let's take y equals x squared plus 1 from 0 to 2. Let's revolve that around the x-axis. Okay, let's revolve that around the x-axis. Okay, and let's find that volume. Now again, let's look at this formula. Why does this give us volume? Because this is area times thickness. Area times thickness, right? The dx is the thickness or the width. You take area times thickness, that gives you volume, right? It's going to be like centimeters squared times centimeters. That's going to be centimeters cubed. Okay, and so hopefully we can always come back to this lemon experiment. We can think of that. We said, okay, we added up 6 slices, but this is going to be adding up an infinite number of slices. Okay, so that dx really is important. It really represents something. So it's weird for us to be doing volume and have to do an area equation in there, but it shouldn't be that weird because, like I said, in geometry, we had that formula for volume, and it was this. It was big B times H. And big B was your base area. So you had to find your base area. So that's how we know, a cylinder is pi r squared h. A rectangular prism is length times width times h. Length times width is the area of the base, and then times the height. Length times width times height. Okay? All right. Anyway, so now, what you might do to set up a problem like this is you might do this. Now, probably not. Okay? But if you want to see the 3 dimensions, so sometimes here in the beginning, I will draw this. So what I did is I took this region, and then I just reflected it down below. And then I kind of added some pieces to it to make it look 3-dimensional, just so you can get a visual of it, okay? So we're revolving this region up here around, and now we can see that blue strip that I had put in. We can see, yes, that blue strip is the radius of that slice, okay? So it's like this. Here's my axis of revolution. Here's my blue strip, and it's revolving around the x-axis, and now you can see how that makes a circle. Right? You can see how that makes a circle. And you can see how this blue strip is the radius of that circle. Right? Okay, so I don't know that you have to draw this necessarily every time. I probably would not. Okay, but that's what you're envisioning. Okay, so what I like to do is I like to do this. I like to say, okay, what is that strip? And this is where your top minus bottom and your right minus left comes in. So you're saying, okay, the height of this strip right here is the top y value minus the bottom y value. So it's x squared plus 1, right? Where's that y value? There it is right there. This is stuff we worked on last week. Here's this y value minus this y value. It's x squared plus 1 minus 0. That's r. That's my radius. Now, what's my volume? Well, it's my area of this slice. This slice is a circle. So it's going to be pi times radius squared, and then my thickness, dx, and then that's going to go from where to where? That integral is going to go from where to where? From, it's the same question we were, again, this is, I'm trying to set the stage to help you here. When we were doing the area, remember how I used to always say the strips fill the space? The strips fill the space from 0 to 2. The strips, because, and in this case, it's the slices, right, go from 0 to 2. The slices fill the volume, or fill the solid from 0 to 2. Okay, go ahead and type that in your calculator there. And to be honest, a lot of times we'll just pull this pi out in front. So a lot of times in a problem like this, I'll put the pi out in front, okay, like that. Not a big deal. You're probably going to need parentheses in there anyway, so it probably doesn't matter. But a lot of times we just pull the pi out in front. So it's pi, but I really like to do this here where I write down what r is. I think I put in my strip, I picture it revolving, that tells me, okay, that strip is my radius of my slice. My slice is a circle. The area of a circle is pi r squared. So I write down what my r is, and r is always going to be a function, because think about it, every slice is different size. Every slice is different size, so every slice has a different radius. And so that's why your r is not a constant. It's this function right here. Okay, what do you get? Yeah, I just leave it in terms of pi, I think. 206 pi over 15. And you don't even need units unless they tell you, but usually we don't. Okay? Cubic, whatever. But 206 pi over 15, yeah, I would just leave it in terms of pi, absolutely. Okay? All right, so let's try one more. So it says this. It says, if you had a problem that said this, it says the first quadrant bounded by y equals square root of x minus 2, x equals 3, and x equals 5. So again, this is the same terminology we've been talking about last week, but the difference is we wanted just the area of that region, right? Okay, now let me just pause here just a second. When we just want the area of the region, don't write this down, well then it makes sense that what we're adding up is the area of each of these strips, right? So let's think back to what we were doing before. We were saying, okay, to find the area of this region, now it's easy because it's on the x-axis, but we said we just want to add up the area of those slices. Well, what's the area of a rectangle? It's length times width. So the length of that rectangle is top minus bottom, so that would be square root of x minus 2, and then times the width, dx, and then that would be, this is 3, this is 5, and that'd be 3 to 5. So it makes sense that that interval gives us area, right? Because it's the height of the strip times the width of the strip, which is the area of the strip, and we add up the areas. Okay, that makes sense. Well, now we're doing something totally different, right? Now we're doing something totally different. Now we are saying that we're going to revolve this region. We are going to, I don't want to go back to that. We're going to revolve this region, so all of a sudden there's going to be this, right? There's going to be this slice there, right? It's going to be circular because it's going to revolve. Just the act of revolving creates circle slices every time. And all of a sudden this strip becomes what? The strip becomes what? Part of that circle. No, the strip is the radius, right? That strip is the radius of that circle. And what we want, according to our formula, is the area of that circle, right? We want the area and then times the thickness, dx. So I like to write down my radius. My radius is that strip, which would be square root of x minus 2 minus 0. A lot of times it's just 0, so that's easy, but we'll get into some that's not. Okay? So the radius is that right there. And so now my integral is just going to be pi times my radius squared. Now I know square root squared, that would just go away, but I think it's good to write it here so we understand what we're doing. Times dx, and then the integral is from 3 to 5. That's it. That's it. Okay? So we create a strip. We put a strip in there. We look at it. Yep, that's our radius. Now later on, we'll see some strips that aren't the radius that we're going to have to adjust it. So it's not quite this simple all the time, but it really is that easy. And you type that in, and that gives you all. Okay. All right. So for tomorrow, we'll just do. I think it's the next line on there. I think it's LH. I think it's 1, 2, 4, 9, and 10. It's on LH, I think it's page 409 on the LH. Does that sound right? No, it's 419. 419. 419. 1, 2, 4, 9, 10. Okay, so they're pretty simple. They're pretty simple to set up. I don't know, you might be able to do them all in 5 minutes. Yeah, so what's going on? Okay, but we'll get into some more. We'll get into some more where you have to do a little adjusting and a little bit of whatever. That's how we do those.